past president of Singapore Structural Steel Society and also fellow of Academy of Engineering Singapore. I'd like to welcome him, and he'll talk about efficient construction of high-rise buildings.
Good morning, ladies and gentlemen. It's my pleasure to deliver this last keynote lecture. The topic of my presentations will be on prefabricated, prefinished volumetric constructions. In Singapore, we apply it for high-rise building. This research is sponsored by the NRF, National Research Foundations, together with one private company who are involved in constructions. They want to invest in a factory so that we can manufacture houses, and then we try to construct it at the site. The definition of prefabricated, prefinished volumetric constructions is that this has to be satisfied because PCA, there's some definitions of this PPVC. In short, we call it. The module will be fabricated at the factory. This shows you the steel constructions. You have a column and beams and slab. After that, you integrate the sub-assemblies, including ceilings and finishes, including mechanical finishes. Then fittings, interior fittings with walls and tiles. Sometimes we have a washroom. And then finally, we'll transport it to the site. Once you go to the site, there's no place for you to store all these units. Straight away, it has to be hoisted up and connect to form the building itself. So in terms of that, we call it stacking method. Why we want to do that in Singapore? Because we are moving towards the digital constructions. We heard about digital constructions lately in many of the conferences, how the Internet of Things changed the way we do business in constructions. Because in Singapore we have a shortage of labor and limited land use, and therefore there's an obsession for us to move towards a very high productive method of building houses. So this method is part of the DFMA method, Design for Manufacturing and Assembly. And we have a unique place because in Singapore we are building quite a number of high-rise buildings, just similar to Hong Kong situations. Actually, we started this in the 1980s when we built many houses using the precast and prefabricated. Prefabricated for steel, do it in the factory. We bring the individual component to the site and try to assemble together. In precast construction, we precast all the beams, columns, slabs, the individual components. We bring to the site and try to assemble up to form three-dimensional structures, applying in situ groutings. I can say that until now we have 95% of the work we carry out at the factories, only some of the small amount of wet work or welding job to be done at the site. And we are moving now to the new method of constructing, which I introduced, is called PPVC methods, where we try to do more in the factories. So all these PPVC units will be completed at the factories, then we just bring it, transport it to the site, and then leave it to form the high-rise building that we have today. So I try to show you some of the experience that we have in Singapore then before we introduce our research. These are the advantages of PPVC. We move towards the industrializations. We are time-saving. The project has been proven that we save a lot of time on that. Better quality control at the factories rather at the site. We have a government incentive to pack this scheme in terms of land sales. That means we're selling the land to a developer. They are really specified, you must adopt this method. So to encourage people to switch to this method. And they have less cost, less impact to the environment, and less waste. We can control that. So finally lead to the higher productivity. Two types of PPVC module that we're looking at. One is called the concrete PPVC. The other one is called the steel PPVC. They have advantages and disadvantages. Mainly the concrete PPVC is connected by walls. The two vertical wall panels is a load bearing panels here to connect them together. And the steel PPVC consists of 4 columns at the corner. You how to connect the 4 columns, both horizontally and vertically. Concrete PPVC is usually heavier, 20 to 35 tons, depends on the unit size. Steel is relatively light. And therefore we can go for a longer span, which I'll tell you how we reconfigure the plan of the buildings. For construction speed, steel PVC, we have a hook connection, so it's faster to construct. There will be some wet work for concrete PVC, you need to do in situ grouting. But the advantage of PPVC, because they think that they are more durable, in terms of this one you need corrosion protections. And for fire, I think the concrete is lower in conductivity, so less requirement, easier for fire. Here you need the fire protections, additional cost involved. So just to show you some of the rendering to see how the concrete PVC will look like. This is a structure, how it look like, consists of wall. This is a load bearing wall. You bring the bearing wall together apart to each other, and then this is the joint. You insert some reinforcement bar to block the 2 walls. So you will do a grouting at the side to connect the walls together. Vertically, the wall will sit direct on each other. You use a lap bar to lap the reinforcement, and then you do the grouting inside. For steel PPVC, it's relatively easy because the modules under the factory, you fully weld them to form a rigid module at the factory. You bring it to the site, and then you do the connections. I'll talk about that connections later with this steel conference. Some projects have been done in Singapore, and there are more projects coming up over here. And they are done initially using steel constructions. This is a completed project in NTU hostel, mainly for student accommodations. 13-story height, they're using, from 5th story to 30th story, using PPVC, steel PPVC. The productivity, they already constructed this one. They found that there's a 40% saving in labor and 15% reduction in construction time. These earlier projects. So roughly it looks something like that. We construct a concrete. This is a concrete construction, cast institute at the site with a core wall. After that, the core wall will go up, and you start to have a PPVC units delivered to the site and start to stack up onto the transfer slab. Then you stack it up, and the core wall will provide horizontal resistance to the module until you reach the top. So this is just there's not much finishing work, just internal finishes and external finishes will be come ready in the factories, delivered to the site. This is a hotel, Crown Plaza Hotel extension near the Changi Airport. There's restrictions of the height. So it's very suitable for use steel PPVC, and the construction time is only 17 months. Actually, the PPVC units can be from everywhere. This is manufactured in Shanghai and shipped to Singapore, and then you just stack it up. The high productivity, 75% saving in manpower, 50% reduction in construction time. Site safety is very important because it's near the airport. There's a nursing home project, not very high, 10-story, and you can install it in 8 to 10 modules per day. Construction time is only 5 months. In 20% saving in construction time. This is a residential plus shopping mall. Below is a shopping mall. Cast institute at the site, concrete. On top, residential units, they stack it up using the PPVC, 12-story height, from 4th story to 12th story. There are 3 blocks of that. Productivity, 30% reduction in construction time. Finally, the most challenging one is this project. It's a very interesting project because it's go all the height to 40-story now. Currently, almost completed. 40-story high residential building, reinforced concrete PPVC. So usually concrete PPVC is very good for residential, and then steel PPVC for hotel, for student accommodation, for nursing home, or maybe now I consider for industrial buildings. Construction time scheduled to be 36 months, expect 30% reduction in construction time. Despite the height, you can see that people are using a concrete PPVC, finishes or pre-finished at the factory, including window frames. Now, PPVC for high-rise building, I think because we're going taller, so the number of repeated modules expect to go up. You have the cost effectiveness, you have more number of repeated units to be fabricated at the factory. Very similar to the car, once you come out with a model, it keep on coming. Just produce the same car in factories. This will derive the cost benefits. In Singapore, currently the cost of PVC is still 50% more compared with the traditional construction methods. But when we go taller, I think these repeated units will bring additional advantage when you go for PPVC. So how to go high rise? Of course, when you go to high rise, the overall stability, robustness has to be considerations, have to take into consider. Structural engineer will work on the joint. I'll talk about that later. And this show you the idea how the PPVC can be used to form a greater units. This is a nursing room, this is a hospital. With all the M&E finishes plus the beds, you can cut it into different units. Each unit can be manufactured at the factory and then bring to the site, an example, to form a larger room. As you can see illustrate from this side. Transportation is one of the main considerations. You can go to larger units, but once you exceed the length given by the Land Transport Authority, the module transport on the road has to be guided by a table given here. The length usually cannot be more than 12 meters. If you're more than 12 meters, you need to escort. Usually you can only escort it at night. There's a height limit because of some pedestrian bridge on the road. So your design of your module has to fit into the width, especially the height, less than 4.5 meters. And the length, if you go beyond 12 meters, is okay. You need to do escort at night. Lifting is the main considerations when you deliver to the module. A lot of time is spent how to do the rigging, how to lift the units. Because we have to lift the units so that the unit is actually parallel to the ground. So when you go to the side, you try to align it, the units will go straight vertically down so that you can make your connection easier. So on the top figure here, you see that this CG, you leave it. You have to align, tilt, so that CG will align with the center of lifting. As a result, your CG will be actually not horizontal to the ground. You need to adjust the cable so that we can realign, so that the unit actually is horizontal, parallel to the ground. So this will take up time. You need to speed up this process, and there's a problem given to us how to do the intelligent self-balancing and lifting methods. This is a prototype done at NUS laboratories. We purposely put some weight to create a CG which is shifted to the left. As you can see that the module actually tilted over here. They show the module actually tilted over here. So the motor, the winding of the cable at the four corners will automatically adjust so that you align the module so they can parallel to the ground. This is a thing that prototype is quite successful. We intend to lift the module slightly off the ground and let the gyroscope measure the tip angle. Then we control the motor so that you can do the adjustment at each corner, so that the length of the cable change and can be obtained at each corner. So we have some accuracy, how we can achieve this accuracy for installation purpose. So for those who are interested, I think this is a good time to invest on that, this method. And every unit will install with this sensor, so that once you do the lifting, automatically you do the self-balancing while doing the lifting and moving the units towards the location that you want. So weight is very important for transportation and for lifting. If you look at the weight distribution in the module, you will find that the structure itself about 30%. The weight actually comes from the floor and the walls. This will take up about 60%. So you want to save the weight, you have to focus on the wall. So the wall you must use a lightweight partition walls, fire resistant type. And we zoom into the floor material to reduce the weight of the floor. So method to improve the efficiency of PPVC for lifting and for transportations. Use a lightweight floor. Try to use less module. So we go for long span modules yet satisfy the transportation requirement. Conventional concrete PPVC is 6 meter to 8 meter. So we stretch it to 12 meters using steel design. And we can reduce the number of modules, therefore we can reduce the number of columns, number of joints. And third point is that how do we reduce the headroom so that we can integrate all the building services within the structural zone. Finally is the connection itself. That's where the research comes in to address this problem. So for material, we are using the lightweight materials. And US, another of my colleagues is a concrete expert working on lightweight concrete with a density ranging from 1200 to 1800 kilograms per meter cube. You can see that this type of concrete weight, you can reduce the normal strength concrete by 40% weight to 50% weight. So we can reduce the slab weight by close to 50%. So some of my researchers are working on that, how to combine this style of lightweight concrete together with structural steel to achieve composite design for the slab. Then we try to apply it to the PPVC. You can see that the configuration of PPVC is quite important to lay the modules. Left side show you the original short span design. You have columns and show dots, intersection point, you have column locations where you have a different type of module in different colors. How do we rearrange this floor plan to achieve less module and therefore less joint? We focus on these columns here, shown here. These are the columns as highlighted here. We want to take away this column. And below is the floor plan for the 12 story also. You can see how this column. We try to realign the module using reduce the number of columns, remove this column, and therefore we integrate the modules together. These are long span modules. Okay. This is very suitable for steel construction. The left side are designed for concrete constructions. We change it to the steel constructions on the right hand side. The gray area part is the corridor and the lift shaft. These are cast steel, so that we can integrate all the modules together, the core wall, to achieve the lateral load resistance. So the module headroom on the left hand side, you see a conventional building. We have only one beam, column, and then beam. These are clear headrooms. The disadvantage of having PPVC is that the module comes with floor beam and floor slab. On top of that, we have a ceiling beam also. Then we put another unit on top, the upper unit floor beam. You can see there's a gap between the upper unit floor beam and the lower unit ceiling beams. This will take up the headroom. Therefore, if you do the PPVC construction, you end up with taller buildings, but same structural headroom you want to achieve. That's what architect requirement. You have to maintain same clear floor height for every unit. So this is a disadvantage of having PPVC. And you can see that connection actually done within the column in this example. So how do we actually squeeze this headroom? So this shows you the typical construction. You have a beam and slab construction. This is a clear headroom 2.25 meter. And we try to integrate the beam and the slab together to achieve the flat slab design. For steel construction, we use slim floor design, so you can embed the beam in the slab. You can still maintain the same headroom. This will save the height, remove the disadvantage of the PPVC. That is where the NUS PPVC module comes in. It's a composite design. Steel beam, channel, or in rectangular hollow sections. Column, square hollow sections. With or without additional bracing, provide rigidity to the module and provide additional support to the bottom beam. and we have a slim floor. So this is a ceiling, additional bracing, optional, column, RH, column, composite, slim floor, slab, and slim floor beam. This shows the composite design. The conventional method on the left, traditional composite beam with a high headroom. So the slab is sitting on the beams. So we try to put the beam in line with the slab to reduce the headroom. Some of the idea is shown here using shear studs. For column, we do the composite design. For lower column, we can ground it with concrete to achieve composite actions. For upper column, we just leave it as a steel column design. So this shows you some of the idea of the U-shape composite infill. These are hollow sections. When you cast a concrete, it tends to cast a beam together. We do the mold. This mold will be created on the floor in factories. So you just cast a slab and the beam together, and embed the beam into the slab. The holes on the whack of the steel beam will provide shear key. You can remove some of the shear studs. Another better choice is to have an inclined surface on the right hand side so that the concrete actually bear against the steel surface. The bottom plate will have supports. Additional fire reinforcement can be provided inside the beam so that you do not need to do fire protections for the steel beams. And you can introduce holes, hollow slab design into it to achieve further weight reduction in addition to the use of lightweight concrete. So this slab will be more than 60% lighter compared to the solid concrete slab. For column design, do we have a problem about how to connect a module together if the column size is different? For low-rise, at the lower level of the building, you have a very large column size. When you go up, the column size gets smaller. So end up with connection problems. You have to connect a very large column to the smaller column, and then slowly the connection detail will change when you go up to the building. Alternatively, you can use multiple columns and adopt the same connection detail shown on the left-hand side. The right-hand side shows you that we can use the same column size throughout the whole building. Up to 40 story to 50 story, we can use the same column size. We use the hollow sections. Below, we infill with high-strength concrete, exploring whether you need to use a high-strength steel or not. Then in the middle level, we change to a normal steel, and yet we can reduce the concrete grades slowly when you move up to the upper floor, where you may not need any concrete inside. So this additional detail we are exploring the use of what we are very good at to design the PPVC high-rise building. So the method, how to use the high-strength materials and high-strength concrete have been published, and now the design guide has been issued. You can use high-strength steel up to 550 and concrete strength up to 90 for high-rise building constructions in Singapore. So the connection becomes the key. You have to stack up the building horizontally and vertically to connect them together. So the connection determines the speed of constructions and affect the overall stability and the robustness of the building. These are connections are not so robust, and under horizontal load situations, we actually topple one by one. So we have to avoid that. And this is a way that we should do it in high-rise building constructions, looking at the connections. So let's take a look on the steel PPVC connections. Basically, the module itself is fabricated at a factory. We can do the welding at the factory and have a good quality of weldings. So they are considered as a rigid connection between beam and columns to form the module itself. You bring to the side, you need to connect to the core wall. So we have to embed these plates with the anchor bar pre-embedded in the core wall. And you bring the units very near to it. And then you do the side welding. You weld the units, the beam onto the core wall. Show you some of the illustration how to do it. Just downhand welding and cheap quality welding on the side. This is a location. Then finally, inter-module connection means the module connect horizontally to each module and vertically. You identify three types of joints. Joint 1 is called a corner joint. It involves actually 2 floor beams and 2 ceiling beams together with 2 columns to connect. The edge joint and the internal joint is the most complicated. It involves with 8 floor beams, 8 ceiling beams, and 4 columns into the joint and tie them together. And this joint they cannot separate. These components, you have to integrate them together. So this shows you an illustration of internal joint. It's so complicated. It involves 4 modules on the top and 4 modules at the bottom. So that's how you can achieve it. And the robustness of the column is very important. Any loss of one column, there will be no toppling down of the modules. So this just illustrates to you some of the method how we can do it. The rebar that provide continuity vertically, and the tie plates actually tie all the adjacent modules together. It's a very simple concept. The detail actually a little bit more complex. We can develop the details. This is one of NUS PPVC board connections. We file patent for that now. This show you the connections. This show you the tie plates that provide shear resistance in both directions that tie all the modules together. Then the rebar basically is to provide tension resistance. There's no loss of column will not lead to the upper 4 module to come down. So there's a vertical continuity. Compression will be direct bearing, and there will be a shear key also to take the shear force due to bearing. This is able to connect the floor beams together. It will enable torsional resistance. To show you the possible of grouting it, you can grout the column and then insert the bar. Then you do a bar extensions, bar lock, put it in to lock the bar, put in the tie plates, connect the modules together to the adjacent modules. Then you do the bar extension, then you lower down the upper units down, and then connect to the bottom units through the beam connections. Right, so you just connect them together, the upper and lower units. This show you how we stack up the modules. The beauty of this method is that we consult the contractor. They do not want to send the worker outside the unit and do the bolting. Everything must be done inside the units and for the safety of the workers. So this enables us to do it where the worker is inside the units and do the bolted connection. There's a panel that's opening. Later we will catch up this opening after they bolt it. The modeling of PPVC connections is almost time, 3 minutes. So I will just say that we have to do the computer modeling, 3-dimensional approach, how to put the spring model, the hinge, and the rigid joint, how to model the tie plate and tie rods together in the model. This is a semi-rigid analysis, which all of us are very good in, and modeling inside frames. We put in the computer and model it, but the problem is that the PPVC, the floor is not continuous. There are individual units, they only connect at the 4 corners. So for floor, the rigid diaphragm cannot be achieved for the entire floor. What we call this is called a discrete diaphragm. The discrete diaphragm is applied only to the module itself. We have to connect them at the 4 corners. Okay, so the numerical modeling is a bit complicated, but it's okay, we can do it. So we can actually do the modeling of the diaphragm, discrete diaphragm, together with semi-rigid joint, and do the analysis. We can load displacement, satisfy the drift requirement, or the ultimate strength requirement. We even go for robustness analysis, remove the corner column or additional column at the base, the entire structure will be safe. So these are the details that I have no time to go into it. Compared to the conventional method, they do have a little bit more increase in vertical displacement when you remove the corner column for the PPVC construction. But it's okay, the building will survive without one of the columns. For fire, we have to seal up all the gaps between the modules. We cannot afford to have these gap connections. We work on the material to reduce the weight, and we propose a slim floor system to further reduce the weight of the slab. And we do the modeling. We come up with interesting connections. We can do it fast at the site and do a model to ensure that the building be safe. Currently, we are working on new connections that do not need any bolts and welding at the site. So people are questioning how we can achieve it. I think I will leave it to the next conference to present this new invention. Thank you very much for it.
Thank you very much.